So today we're going to be going more into graphing of logarithmic functions. So what I want you guys to do for the do now is just find the inverse of y equals 2 to the x, then graph y equals 2 to the x and its inverse on the graph to the right. Pause this video, just to take about 3 to 5 minutes, and play it again once you're done. So if we want to find the inverse of y equals 2 to the x, that means first thing we have to do is, instead of it being y equals 2 to the x, we need to swap the x and the y. So it'll be x equals 2 to the y. Then we gotta solve for y to get y by itself. So the y is the exponent here. So in order to get the exponent by itself, we have to use log. So the base is 2, as that's the base on the exponent. Our exponent is y, so we say equal to y, and our argument is x. So that is our inverse. Now, what we want to do is, on the side of axis, we're going to graph y equals 2 to the x and its inverse. So when you graph y equals 2 to the x, just plug in some numbers in for x that are easy to graph on the graph to the right. I chose -2 to 4. Plug those in for x, get the corresponding y values. So that would be the points I'm going to plot for y equals 2 to the x. And I think the easiest way to graph y equals log base 2 of x is just to take its inverse, which is y equals 2 to the x, and swap the x's and the y's. So we're going to swap the x's and the y's for every single point. So the first point, instead of being -2, 1/4, is now 1/4, -2. And you do that for every single point. So since the inverses are swapping the x and the y, we are allowed to do that once we get to just the xy table. So now your graph for y equals 2 to the x should look like this, and your graph for log y equals log base 2 of x should look like this also. And one thing you should notice, since they are inverses, they should be a reflection over the line y equals x. You don't have to graph this. I'm just including it just to show you guys. They should be a reflection over the line y equals x, which they are. So that is how I would go about graphing y equals 2 to the x and y equals log base 2 of x. You could also graph these in your calculator and just double check it. They should look like this. And what should I know by the end of the day? So I can describe how a logarithmic equation is being transformed. It's just how everything else is being transformed. You guys are going to see that in a little bit. I can graph a logarithmic equation that is undergoing multiple transformations. So moving up, moving down, left, right, reflection. I can determine the asymptote of a logarithmic equation. I can determine the domain and range of a logarithmic equation. We've worked with those before. I can determine the x-intercept of a logarithmic equation. I can determine the end behavior of a logarithmic equation. And I can graph a logarithmic equation with a base such that it is in between 0 and 1. So let's go to the next page. So we're going to look a little bit more into the graph y, or f of x, equals log base 2 of x. So here's the graph. I also include the xy table on the left. Let's take a second. I know we've done this already, but let's do, on a previous, I think it was a couple days ago, let's just do the domain, range, and the asymptote and the x-intercept for this. So pause the video, take a minute, and write those down. So remember, the domain is all possible x's. So if I look for all the possible x's here, I look to the left, and as far left as it's going is 0, but remember, it's not going to be 0, so it would go from 0, and then far right is the greatest x's. That keeps going on to infinity. Ranges is the y's. So with the lowest, how far it's going down, it keeps on going down, so go to negative infinity. How far it's going up, remember this is going up slightly and more slightly as we increase in the x, so that would be to infinity. The asymptote is the line that does not cross. That would be it's not crossing the y-axis, which is the line x equals 0. And the x-intercept, remember the x-intercept is where it crosses the x-axis, and this is important. That's when the y is equal to 0 is where it crosses the x-axis. So that point is right here, and you can also look at the table. It has the point here. It's when the y or f of x is 0, so that would be 1, 0. Now, end behavior might be new, so left end behavior and right end behavior. So it's similar to looking at the domain and range, but it's just looking at the end behaviors. So as x, if I look at the left, so the leftmost side of this graph is here. That's the most left we're getting. I know it keeps on going down. It keeps on going slightly more to the left, but never crosses 0. So this is red. The arrow there says as x approaches blank. So what is x approaching on the left side of this graph? It's getting closer and closer to the value of 0, but it's actually not becoming 0. So as x gets closer and closer to 0, or what we say is as x approaches 0, f of x, or y, is approaching, well, it keeps on going down, down and down, so that would approach negative infinity. And the right end behavior is over here on the right side of our graph, the rightmost that this is becoming. So as x approaches, x does not have an asymptote on the right. It's not stopping it. So x is going to continue on towards infinity. What is f of x going to approach? Well, it's going up. It's going slightly up. Each as x is increasing, but it keeps on continuing going up without bound. So f of x would approach infinity. So left end behavior, you would read it as x approaches 0, f of x approaches negative infinity, and the right end behavior is as x approaches infinity, f of x approaches infinity. You will also see y written here sometimes too, but usually it's in function notation. So that is a little bit of looking deeper into this graph, but now we're going to look at transformations. So now we're going to graph these three equations. And it's exactly the same as, the transformations are exactly the same, very similar to when we did quadratics and polynomials, absolute value. They're all very similar. So I want you guys to take a, take a minute or two, and I'll see if you guys can describe how each transformation is changing from its parent function or the original equation, if you want to think of it like that. How is each graph, so g of x, h of x, and k of x changing from f of x? Take a minute, pause the video, and see if you can think of how it's going to change. So, if I were to look at the log base 2 of x plus 4, what would happen if we added 4 on the inside with the x? If it was like quadratics or absolute value, polynomials, well, it's with the x, so you go left or right. And if it's plus 4, it would go 4 units. And then since it's plus 4, it would go to the left 4 units. How about log base 2 of x plus 3. Well, the plus 3 is on the outside of the x, is not inside with the parentheses. So that's going 3 units. Since it's plus, it's going 3 units up. And that last one, if you multiply by -1 on the outside of everything, that's when you have a reflection over the x-axis. So let's graph each of these. We can check out the domain range and asymptote also, but it might be easier to graph it first. So let's use the same. I'm going to try and color coordinate it. So let's use the same colors. So g of x is purple. So let's go back up to the top here. So I'm going to do an xy table for g of x. So if I have g of x, g of x was equal to log base 2 of x plus 4. So if we're saying this is just sliding or translating all of the points to the left 4, that means if our original point was at 1, 0, if I move 1, 0 to the left 4, and I'll do that here, 1, 0, to the left 4, that'd be 1, 2, 3, 4. That would be at point -3, 0. So essentially all we're doing is we are subtracting 4 from all the x values. And we can do it again with 2, 1. So 2, 1's here. We're going to go to the left. 1, 2, 3, 4. And there would be 2, 1. Sorry, it'd be -2, 1 now. And you can do that with every single point. So you're subtracting 2 from the x, and the y stays the same because it's just moving to the left. So this would be 0, 2. Then 4, 3. And then if we were to do that one more, that would be 12, 4. And you guys are more than welcome to also check and graph this in your calculator if you want to. Let me just get those points out of the way. So I'm going to graph that. So we have here 0, 2 would be here. 4, 3 would be here. So it would look like this. And since it's moving to the left 4, our asymptote is no longer x equals 0, like it is for just the parent function log base 2 of x. If it's moving to the left 4, our asymptote is now going to be at x equals -4. So we're not going to want to cross that x equals -4 line. So that would be g of x. Okay, so let's do the domain, the range, the asymptote for g of x. So if I look at g of x, I think maybe the easiest thing to see here is the asymptote. So the asymptote is no longer x equals 0. It's going to the left 4. So 0 minus 4 would be -4. It's not going to cross -4. So it's not going to cross x equals -4. That would be our asymptote. If you look at the graph, the lowest point still going for the range is still -infinity to infinity. The domain's changing a little bit. So the domain, the lowest possible x we can have is just right before -4, but it's not going to be -4. So it'll be parentheses -4, and that's still going all the way to the right to infinity. Let's take a look at our x-intercept here. Remember, the x-intercept is when y is equal to 0. So I'm going to set the equation equal to 0 over here, and you can also see it by the table, but I just want to show you guys how to also do it algebraically, because you're going to have to do that for some of the questions coming up. So it would be 0 equals log base 2 of x plus 4. Let's solve that. Let's put it into an exponential form. So I know my base is 2. My exponent is always what the log is equal to, which is 0. And that is equal to the argument, which is x plus 4. 2 to the 0 power, anything to the 0 power is 1. 1 equals x plus 4. Subtract the 4 on both sides. You would get x equal to negative 3. So our x-intercept would be negative 3 is the x. Remember, the y is always equal to 0. As you take a look, our x-intercept is negative 3, 0. So that checks out. Now the left behavior, look to the left. So as x approaches, as we look to the left, x is approaching negative 4. So as x approaches negative 4, the y, or I guess it would be g of x in this case, the g of x continues to go down. So that would go to negative infinity. And the right behavior, if I look to the right of that, the right behavior is as x, the x keeps on going to the right. So as x approaches infinity, g of x or y is going to approach infinity, just like the parent function log f of log base 2 of x. I want you guys to try h of x. Try and do h of x all by yourself. Do the xy table, and then do the domain range, asymptote, x-intercept, left-hand behavior, and right-hand behavior. Take 2 to 4 minutes for this. So I did h of x in green. So remember, we're going up 3 units. So if you just look at any point, let's look at 1, 0 again in our parent function. Y equals, or f of x equals log base 2 of x. If we take y 1, 0, if it's going up 3 units, that's in the y. So up, we would add 3 to 0, and you would just get 3. So as you see, we do have 1, 3. And that's what you just want to do with every single point. You could also graph in your calculator and check out the table. So that's what the graph would look like. Now let's talk about the domain and range looking at this. So the domain isn't changing. It didn't move left or right from the parent function. So that's just going to stay still. It's not crossing 0 for x. So it's still going from 0. We don't include the 0 because it's not crossing 0 to infinity. The range, although it's moving up, the range isn't changing. It's still going to infinity and negative infinity. The asymptote, still not crossing x equals 0. The y-intercept is going to change a little bit. So you could set it equal to 0. So that would be, set our equation h of x equals 0. Because remember, the x-intercept is when y is equal to 0. So this would be 0 equals log base 2 of x plus 3. First thing you would want to do here, we want to get the log, the x by itself. So you got to subtract 3 on both sides. And you get negative 3 equals log base 2 of x. Now we can put this into a exponential form. So our base is 2. Our exponent's what it's equal to. Negative 3 equals our argument, which is x. And 2 to the negative third would be 1 over 8 equals x. If you were to continue our table, we would have seen that 1 more because we went to 1/4. So our x-intercept is at 1 over 8, 0. X-intercept of y is always equal to 0. And the left-hand behavior, so the x is, the x is still on the left. If you look at the green function, the most left is going is 0, but it's not crossing 0. So that's going to be as x approaches 0. Y is going all the way down, so the h of x, in this case, would approach negative infinity. And the right-hand behavior, not changing. That would be x is approaching infinity because it keeps on going to the right without bound. The g of x, or the y value, scroll down so you guys can see that, is approaching infinity. So those are those two. If you guys want to try k of x, go right ahead. Pause it. and give it a shot. I'm also going to go over it too. Looking at its reflection over the x-axis. So I'm going to come up here and do a table for k of x here. So k of x is equal to negative log base 2 of x. Remember, that's a reflection over the x-axis. You're more than welcome to graph this in your calculator, but let's use what we know about reflection. So, if I'm going to reflect over the x-axis, let's take a look at how that's going to affect our point. So, for example, let's say if I have, I'm just picking a random point. This is not going to be actually on the, not on the graph. So, if I have, I don't know, here is 6, 1. If I have 6, 1, I'm reflecting it over the x-axis. That is now going to become, the x doesn't change, but the y now changed its sign to becoming negative. So that's what's going to be happening with all of our points. So if I look at our original points for f of x, let's take 2, 1. So 2, 1 is right here. That's now going to become 2, negative 1. So all of our f of x's are just going to change signs, including up here are now going to be plus. And the 0 just stays the same sign because 0 doesn't have a sign. So that would be 1/4, 2x, or positive 2, excuse me, 1/2, 1, 0, 1, 0, 2, negative 1, 4, negative 2, and 8, negative 3. So when I go to graph it, so there's the graph of k of x if you plot all the points. Let's take a look at the domain, range, asymptote, and the end behaviors along with the x-intercept. The domain, although it's getting flipped over the x-axis, it's not being changed at all. The domain is still 0 to infinity. Oops. Still 0 to infinity. The range is definitely going as up high as infinity, but it's still progressively going down to negative infinity with the range, so that's not changing. The asymptote, still not crossing x equals 0. The x-intercept, if you look at our table, that's also not changing. That's also not changing, so that's still from log base 2 of x equals f of x. So that's still going to be, oops, 1, 0. Now the end behaviors are definitely changing, so look as we go to the left of k of x, as we get to the leftmost of k of x, x is approaching 0, it's never going to be 0, and k of x, or y, is going up. So it's going to approach infinity, and if I look to the right of k of x, x is approaching infinity, but the y value, the output k of x, is going down, so k of x is going to approach negative infinity. So that's a lot into dissecting the graph of a logarithm and the transformations. So on the next page, I want you guys just to take, 2 to 3 minutes and do 1 through 6. So describe how f of x equals log of x is changing or changes to form each of the following equations. Press pause if you haven't. All right, so I'm going to show you the answers to that. Number 1 is translating right units because it's -6 with the x, so it's going left to right. It's minus, so it's going to the right. 2 is down 9. 3 is left 1 because of the plus 1. Up 10 because of plus 10 on the outside. Reflection over the x-axis for k of x, which is number 4. And then 5 and 6 also. So, what I want to do now is and I want to look into graphing this equation without using a calculator first, and then we'll show how I'll show you guys how to graph in your calculator. Although we've already went over it. So if I want to graph this equation in the calculator, so if I want to graph this without a calculator, the main thing here that we need to think of for a nice, so I'll do an XY table over here, X, Y. But it might be tough to see what the nice x's are going to be. So x is with the log base 2 of x plus 4. So I'm going to go off to the side. If I know we have log base 2 of, let's just say, any random number a, what are going to be the nice numbers that I can put in for a to get, which in this case is our x, but let's make that x. So what are the nice numbers I can put in for this equation's x, or expression, I should say. Now I'll make it an equation, in order to have a nice y value. So we're graphing nice points. So remember, the y is always, what's on the other side is always the exponent. The x is the, in this case, the x is the argument. So x is really just the powers of 2. So we're going to want the powers to be, let's go for, 1, 2 to the 0 power, then 2, 4, 8, 16 are the nice numbers to use for this. But the main difference is it's not log base 2 of x. It's log base 2 of x plus 4. So we want x plus 4 to equal these numbers here. So what would I plug in for x in order to get the nice number of 1, which would be 2 to the 0 power? Well, I would want x plus 4 to equal 1. What would x have to be? Subtract 4 on both sides. X would have to be negative 3. So over here, I'm going to want my x to be negative 3. And let's do the next one for, we want that inside to be 2. How do I get that to be 2? Well, I could do x plus 4 equals 2. The x has to equal negative 2, and you can just go down the line doing this. In order for the argument to be 4, well, x would be 0, because 0 plus 4. In order for it to be 8, you want to do 4 plus 4. In order to be 16, you want to do 12 plus 4. So that's how I'm going to go about getting my x values. And then from there, you just want to plug them in to the equation. So, and I'll do one of the points over here. So let's do negative 3. So that would be log base 2, x is negative 3, plus 4, minus 3. So that would be log base 2 of 1, log base 2 of 1 minus 3, log base 2 of 1. Remember, anything with the argument of 1, that's going to equal 0. So that would be 0 minus 3, so that would be minus 3. So the first point we would plot would be negative 3, comma negative 3. I want you guys to try, we'll do one more. No, I want you guys to take it from here. So try and figure out the next points and graph it and answer this describe the behavior question, please. So pause it now, take 3 to 5 minutes, and do that. So I'm going to show you what it should look like. So it should look like this. I plot the points. Remember, it can't cross. This would be x equal to negative 4 would be the asymptote here. So it's not going to cross negative 4. And let's take a look at how to do this in your calculator. So if I were to do this in my calculator, I'm going to go to y equals. I'm going to graph, well, it's already got there, but we'll go to math, go down to log base. If you have a TI-84, press enter. It'd be log base 2 of x plus 4. Then get out of the parentheses. We got to subtract 3. Subtract 3. Press enter. Graph. That's going to look like that. Make sure you know that the logarithmic equation is not cut off there. It actually keeps on going down. The calculator doesn't show it. So when you check out the table, a little bit easier to see those points. It's all the points that we have here, right there. And as you can see the graph, let me show you the graph. Same exact thing. So that's another way of doing it, but I don't want you guys to use a calculator because it just helps you remember it more if you don't use a calculator. So describe the behavior here. Oops, wrong page. So if I'm describing the behavior as x approaches -3, so as x approaches -3, and as x approaches positive infinity. One second, that shouldn't say -3. Let me change that. It should say -4. So I'm going to change that to -4 because -3 is not the end behavior. It approaches it at -4. So as x approaches -4, what is happening to the function? Well, f of x is just, let me make sure it was named f of x. Oh, it was y. So we can just say y is approaching, it's going down, and it's going to continue to go down. So it's going to approach -infinity. And as x approaches positive infinity, if we look how it's going to start to level out, but still going to keep on increasing. So y is going to approach infinity. And there you have it for this page. That's it. Next page. So on the next page, let's take a look at when the bases of the logarithm equations are different. So for this case, we've been graphing only when the base on a logarithm is greater than 1. So let's take a look at why the ends of the graph actually behave like this. So if I'm looking at the left end of the graph, that is, let me highlight it. The left end is the left of the graph, so that is this region right here. So if I'm looking at the left end of the graph, why is it behaving like that? So I think the first thing to do is, I think it's easier to look at in exponential form. So here is the logarithm form of our equation, log base 2 of x equals y, and I'm going to look at that in exponential form because I think it's easier to think of in exponential form. That's what we're used to using more often. So if we look at the left end, we can either look at when y is getting smaller, closer to -infinity, or we can look at when x is getting closer and closer to 0. I think it's easier to see as x gets smaller, so as x approaches -infinity. I think it's easier to see when y approaches -infinity, not x. X is approaching 0. So let's think of it as when y gets smaller and smaller. So I'm going to first say, let's look in the negative direction, because that's where the y is going. It's going down to -infinity. So let's look at when y is equal to -1. So 2 to the negative first power, well, that is just equal to 1 over 2, because you flip the base. Okay, let's get smaller than -1. Let's do -2. So 2 to the negative second power is 1 over 4. So we're going from 0.5 to 0.25. So x is getting smaller and smaller. How about when y is -5? When you plug 2 to the negative fifth power, you get 1 over 32, which is smaller than 0.25. And let's do -10 for y. When 2 to the negative 10, that is 1 over 1024. As you see, the x value is getting closer and closer and closer to 0. It goes from 1 over 2 to 1 over 4 to 1 over 32 to 1 over 1024. But it's never actually getting to 0 because you can't make the numerator 0. It's just making the denominator larger and larger, which is getting us closer and closer to 0. but never actually hitting 0. So that's why the left hand is behaving like that. And let's look at the right end. So if we look at the right end, we're using the same thing, and we're still going to look at 2 to the y equals x, keeping its equivalent exponential form. So if we look at the right here, so if I look at the right, that is when x is getting closer to infinity. So let's just start with the positive number. Let's start with 2 to the first. So if I look at 2 to the first, that's equal to 2. Let's keep on making that x larger and larger. So let's look at 2 to the third. That's 8. How about 2 to the 10th? That's 1,024. How about 2 to the 20th? So as you see, our x is our argument. It's what it's equal to. Our y, so our x is our argument. Our y is the exponent in this case. So as you see, the x is getting extremely large, but the y is getting large, but not nearly as large at the same rate the x is getting. So as the y gets larger and larger, the product x gets exponentially larger. It's increasing more in the x and the y, but the y is still getting approaching positive infinity, and so is the x. So let's take a look at, it behaves a little differently. So the base here is greater than 1. If the base is in between 0 and 1, you're going to see the graph's going to look a little different. There's a reason for that, so I'll make sure we go over that. So I want you guys to quickly graph log base 1 over 2 to the x. Take a minute and try and graph that. Use an XY table for that. So your table should look like this. I know it's a little weird because the base is 1/2, but I start off with if x is 1, then if x is 1, we know if the x is 1, the argument's 1, the exponent is always going to be equal to 0 because anything to the 0 power is 1. And then I said if the x is 2, because it's easier to graph when x is 2. Easier to graph, just like nice number to graph. When x is 2, that's when 1 over 2 to the, let's put this into its exponential form. It'd be 1 over 2 to the y equals x. So when y is -1, which is in this case, that's when you flip it and it becomes 2 over 1. So that would be the x would be 2. And that's what we do with all of them. So 1/2 to the -2nd, 1/2 to the -2nd would be 4. So that's why it's 4 comma -2. And you keep on going from there. So now I would graph the points. So the graph should look like this. And as you see, it looks a little bit different from when the base is greater than 1. So why does it behave like this? So I think the best thing you could do to understand it is, so here's the logarithmic equation. Let's turn that into the exponential because it's easier to think of. So let's think about it as when x is approaching 0. You could also think about it as when y is approaching infinity, because that's the left end here. X is approaching 0, y is approaching infinity. We're going to think about it as when x approaches 0. So when x approaches 0, let's start with when x is 1. When x is 1, well, the y has to be 0. Let's say when x gets closer and closer to 0. So I'm going to go when x is 1/4. What happens to the y? So when the x is 1/4, the y is 2 because that is 1/2 squared is 1/4. How about when the x is closer to 0, we'll say 1/8. That would be 1/2 to the 3rd power. So that y is getting larger and larger. How about when x gets to be 1 over 1,024? That would be 1/2 to the 10th power. So as you see, the y is increasing to infinity as the x gets closer and closer to 0. So as the product or argument x increases, the exponent y increases when the x decreases, the exponent y increases. That is because the base is less than 1. When you multiply more numbers that are less than 1, the product is just going to decrease. When you multiply by a number that's less than 1, the number is going to decrease. And let's look at the right end. So the right end, we'll also see that the x, if you look at the right end, that's when the x is approaching infinity. So as x approaches infinity, let's start with when x is 1. So when x is 1, we already did this one above. The y is 0. How about when x is 2? When x is 2, the y would be negative 1 because 1/2 to the negative 1 is 2. How about let's get a little larger. Let's make x equal to 8. You see the y, the exponent's getting smaller and smaller when the x is equal to 1024. The y becomes negative 10. So as the x approaches infinity, the y is getting smaller. So that's why the y is approaching negative infinity. And that is because as the value of x increases, the exponent decreases, the y. That is because when the exponent is negative, think about it, the base is flipping. So when it's flipping, the x is going to be increasing, but when the exponent is staying negative, and say we had 1/2 to the negative 20, that's going to make a large argument, but the exponent's going to be getting more and more or less, which is why the y is approaching negative infinity. So y would be the equivalent exponent in this case. So on the next page, I just want you guys to do the success criteria, and then there's a classwork after it.